In this video, I will demo our recent paper called Scheduling Big Data Workflows in the Cloud Using Cultural Algorithm. We call it the CAS from now, so it stands for Cultural Algorithm Scheduling. So mainly we plan to use a cultural algorithm to come up with the optimal scheduling solution to run a workflow execution in the cloud. So here you can see the cultural algorithm figure. It contains or includes two main components, belief space and population space, as well as some interface function like accept, influence, select, update, and so on. So in our example, we will see how we make these two components and how they communicate to each other. So in this section, system model, you can see the definition. So cloud environmental definition includes resources, types, and resource usage time, data consumption rate function, FB, and so on. So we have a definition for big data workflow. It contains four tuples: workflow task, and data set, and two function, execution time function and data size function. And we have another definition called task mapping M. So in the first step, our algorithm create a task mapping M, like here in the example, for example, is a vector of the number of the task. The size of this vector is the number of the task. So 1, 2, 1, 2, 3, 1. So here in this example, once means we mapped task 1, the first task, to the VM1. So the indices is task number, and the values are the virtual machine number. Here there is more definition. Big data workflow graph G. We have more definition about the actual start time, AST. So given a workflow graph G and the task map M, the actual start time of the task TK on a resource M TK denoted by AST TK MTK is the actual start time when all procedures have completed their execution and all input data have arrived at resource MTK. So these are the procedures of task TK. And is officially defined by this formula. So if it is a T entry, the actual start time is 0. If it is not a T entry, and the actual start time is the maximum of actual start time of the parent of TK, as well as execution time of the parents, and transfer time, and also get avail time for the machine which we plan to run task TK, because sometimes maybe the data is ready, everything is ready to run TK, but the corresponding virtual machine is not ready, it's busy with doing some other task. So the maximum of them is the actual start time of task TK. So here also there are some like a initial condition. For example, execution time of T entry is 0. So usually T entry and T exit are dummy tasks. Or transfer time of a task, if they are in the same machine, so it's 0. We don't need to move any data. And so another definition is actual finish time of time of task tk, denoted by this one, which is actual start time of task tk plus execution time of task tk is the actual finish time of task tk. Then once we have it, we define the workflow max span as the actual finish time of the last task txit. Also, we have a definition for actual task execution cost. So T.A, definition 2.8 and 2.9 are two definitions for the cost corresponding to task execution and the data transfer cost. So actual task execution cost TK and mission MTK is the size of the TK divided the cost that is associated for machine MTK. And for the data transfer, if it is the same machine, the cost is 0 because there is no need to transfer data. But if it is a different machine, so based on the size of the data and the data transfer rate between two machines, MTK and TK1, you can calculate the actual data transfer cost. Okay, once we have it here, we need to fix it. The workflow cost, the total cost, here actually should be the summation so here is the summation. You can select these items. Good. Okay, this one is a summation of all the ATC plus ADC for all the tasks. The task belong task of the workflow. For all the tasks TK belong to the workflow G, the total workflow cost is ATC, actual task execution cost, plus actual data transfer cost. Okay, and this definition defines our fitness function FS score. Suppose M is max span, so for max span we have WMF, and for cost we have a WCO. Is cost, and the D is a provided deadline. The FS score is defined as with this formula. We have two conditions. If the solution meets the deadline, then we calculate it by this formula. We try to normalize them, and if the solution meets the deadline, we give them a score between 0.5 till 1. And if they don't meet the deadline, it means we cannot find that solution. So then we don't consider the cost, and we just consider the deadline divided by workflow max span. So if we don't meet the deadline, we try just to give the solution that is close, the first solution which is close to the deadline. And the max cost here is the total workflow execution cost once we map all the workflow tasks into the most expensive cloud virtual machine. So this max cost is not the max cost of a solution in each population, and we consider a max cost once we have the workflow. Supposedly we give all the tasks into the most expensive cloud virtual machine and then run it, and then we come up with the max cost. It means if we give them the workflow task to, for example, for all the best machine, which are the most expensive machine, we cannot pass this max cost. So this max cost then it will be fixed for each iteration. And this is the workflow cost minimization. Given a workflow W in a cloud environment C and deadline D, the goal is to find workflow scheduling such that workflow cost is minimized and workflow max span meets the deadline less than or equal to D. Okay, this is the first table of the notation. Here you can see also the structure of the situational knowledge and normative knowledge. The situational knowledge is the elite, the best solution in each iteration or in each population. So x1, x2, xn is like a solution or map. So T1 is going to x1 and so on, and fx is the fs score. So we have a normative knowledge. So the belief space includes two knowledge in this paper: situational knowledge and normative knowledge. And this is just a structure of normative knowledge. We have the elites, and for each elite for each task, using the elites we add the minimum virtual machine number and maximum of it, and we add the fs score associated for each of them. Okay, this section is talking about the algorithm. Here you can see the flowchart of our algorithm, and we use one example with these 7 tasks, and also we use some numbers. These are a list of the class resource parameters, which is the real numbers for each machine. Suppose these are the type of the machine, and these are the number regarding the CPU, number of ECO component units, and also the cost per hour. So let's follow an example. Suppose we have this example, and we have a 500,000 seconds as a deadline, and we have this information regarding the cloud resource parameters, and these two information about the task computation and the data dependency, the size of the data. So in this algorithm we run first, we run a paradigm of the workflow, which I will explain later, to get the number of the VM, and also we parse the workflow specification to calculate the number of tasks, which is here is 7 total number of tasks. Okay, so in the first step, we create the first generation randomly. So these are the 5 of these solutions. Supposedly we have these 5. We can generate more, and then we calculate the fs score and the max span and the cost associated to each solution. Then in step 2 we select, for example here we select to show the elites, we select the 3 top best solutions, which is here is ID5, ID4 and ID3. Why they are the best? Because their fs score are the highest. So situational knowledge is the best one, which is here is the number 5, because the score is the highest. So we add that solution, the mapping actually to the situational. Let's call this as a mapping, maybe it's better. So this is the situational. Now let's make the numerative knowledge. So for each task, T1, T2, T3, T4, and T7, we just go and then see inside the elites and get the minimum and the maximum. So here, for example, for T1, the minimum is 1 and the maximum is machine number 4. We put 1 and 4. And for each of them, we add them the FS score, so the corresponding FS score. And the same for the T2, the minimum VM number is 1 and the maximum is 5. And we select 1 from this solution, and this is the FS score, so we add it for lower bound, and for upper bound we select 5 with 5 from the middle solution, and this is the FS score, so we add it for the upper bound, and so on. We do it till the end. Then we calculate the size is a max number minus the min number. So here is a 4 minus 1 is 3. In for T2, 4, 5 minus 1 is 4. T3, 4 minus 1 is 3, and so on. Once we have situational knowledge and numerative knowledge, we add them, these two, as a belief space. So we actually build and generate our belief space by generating situational and numerative knowledge. So for the step 3, we calculate the task was for each task, and is calculated with the frequent number of the virtual machine inside the elites. So for example, for T1, the first one is a 4, 1, 1. So machine 4, 1, and 1. The frequent of, or the most of them is 1, because 1 is repeated twice, but 4 is repeated once. So we select 1. For task V2, is it 1, 5, 4. 1, 5, 4. So these are tie, and in this case we will select 1. Why we select 1, the first one? Because this is the best solution. Even among the elites, this is the best one. So if there is a tie, we select the machine number from the best solution based on the FS score. So once we have this number, we create the comprehensive elite. For in this case is 1, and then it can be the second task also is 1, and so on. So in step 4, we go and update the population using a belief space. Now once we have a belief space, we will use the knowledge in belief space to direct the next generation. First of all, we create and determine what the DX. DX means like a step. So for the virtual machine, we want to see if we want to change it to go further, forward or backward, or not, just stay in the same machine and don't change. So once we have a solution, we just check it. We must check it if the current virtual machine number is less than the virtual machine number in situational case, which is the elite. So it means we need to direct that solution for the task 1, for example, going to the situational K machine, which is the higher in this case. So we need to go one step forward. The same is the VM solution machine number is the greater than the VM the elite or situational key, so we need to go one step backward. And if the VM solution is equal to the VM situational key, we don't need to change it because it's already select the best machine based on the elite. So here, as you can see, for the previous solutions, by this step we will go and then create a new solution. First, we calculate dx for each task. It can be either 0, -1, or 1. And then once we have this one and the previous solution, we will add these two solutions and dx together and then create a new solution. So 4 plus 0 is 4, 5 minus 1 is 4, and so on. So here we go just one step forward or backward, but if we have a more machine or more options, sometimes we can increase this step. Instead of, for example, 1, we can go 5 steps forward or backward. But here, because our sample is small, so we select one step for 1 unit for our step. So once we have this and the new solution here, we create the new solution, we will go and then do the crossover and mutation. This part right now we added here randomly, but you are going to go to update it and make it a better crossover and mutation, some sort of, like we can call it a smart crossover and mutation. So we will keep you updated our progress about these two functionality in our next presentation. Okay, so this is just a description of our algorithm, and this is just a pseudocode. The pseudocode is updated, so till here we just create the mapping. After we have that mapping, it means which task map to which virtual machine. Then we generate the schedules based on the M and the Cloud VM configuration. And for each pair MK in M, so for each pair means which machine going, which task going to which machine. This is like a pair, right? For example, TK and VM1, yeah, VM, for example, VM1. So T, for example, 1. This is like a pair, yeah. It means T1 is mapped, it should map to VM1. So we insert it with the TK and the machine, and also actual start time and actual finish time. We insert that one into a schedule. And if we need to provision the machine, we add that one also to our schedule. So if the PMJ is new, we will add that one and the provision time to our schedule. And after this one, we add also the provision time to our schedule. It means the actual finish time of the last task assigned to each virtual machine. We get it as a deprovision time of that VM machine, virtual machine, and then insert that deprovision to our schedule. And at the end, once we have this one, we return the schedule as well as the max span of SH, that schedule base one, and the CAS. This max span and CAS is coming from the Mac. So this is the two algorithm paradegree, and algorithm 2 is the update leaf space. So paradegree actually define the maximum number of tasks that we can run in parallel in the workflow graph. So that we calculate by algorithm 1 and this algorithm 2. Okay, so still I'm working on a little bit on like a pseudocode, and then to update it, the pseudocode. It's some effort, it's in some work on it, but it's almost the main steps are there. And the other existing task which I did primary, and the basic step is to do experimental result. For experimental result, we plan to use the Pixels benchmark, including 5 workflow, as you can see here. So we plan to design the structure actually in Montai, CyberShack, Epigenomics, LIGO, and Sift into data view. We are going to go and then create the structure of it. But for each of the tasks, we will go and simulate the task and put some computation for each task. So we plan to use them with a different number of the tasks, because for each of them we can repeat it. For example, for CyberShell we can have 10 of this structure, or for the montage the same 10 number of that, so we can increase the number of tasks actually. So we can have about like 1,000 of these tasks, and we plan to run it like 100 times each time and get the average, because it's a heuristic. So we are hoping the average give us a good solution. And we plan also to check it with 5, 10, 15, 20, and 25 number of virtual machine with 200 terabyte and 1 petabyte of the storage capacity. And this machine also we will work Amazon EC2 based on the table that we put it here. So it can be a real numbers based on the execution time and cost. So we are still working on the experimental, and the first step we plan to compare the CAS algorithm with the genetic algorithm, because genetic also is evolutionary. So in the first step we will compare the CAS with the genetic algorithm, and then based on the other papers we plan to also compare our solution with the other methodology, like a paper 1 and so on. And for now we plan to show the result based on the max span and the cost parameters. So this is we plan to show the performance of algorithm, but also we can show the accuracy actually of the result, or the convergence time of an algorithm compared to the genetic algorithm. But we are working on this part, especially experimental, and by the next presentation we will give you a better and accurate result and description about that. So these are a little bit about the related work. It needs to improve, especially we need to add more evolutionary workflow scheduling algorithm to it. And these are some of the references. Okay, thank you. So for the summary, mostly we come up with the formalization. And the other things we also add a real number for the machine, and update the algorithm. This algorithm, before that it was just a mapping, we make him a schedule. So in the first step is create our placement, task placement in M, but once we have M as a task placement, from here to here we make the schedule and add it like a actual start time and finish time for each task, and deprovisioning to the schedule, and it's written in the schedule. So it's gonna be including the time associated for each mapping. Also for the experimental we plan to design and develop these 5 workflows from Pixel's benchmark to our data view. The structure will be the same, but we will go and then simulate and put some computation for each task. So we can check and then compare our algorithm. In the first step, we compare it with the genetic algorithm, which is in the same category of evolutionary algorithm. But in the next step, after that, we will compare it with more specification. And here, at least, we said we can compare the max span and the cost of it. But for sure, for the next step, we will let you know more concrete and accurate metric, performance metric about that. So mostly we will work for the next step about the experimental. Another thing also, the code is written in R now. I think is a good time to bring it to data view. So first step, we need to develop code to call R package, and for the next step, after that, we can add it to the data view. So in parallel, we are working in that part. Okay, I'm still working on this one, and hopefully by tomorrow also I can give you some also progress in some part of it. Thank you for watching this video.